Okay, it is just about 1 p.m. Eastern US time, and we welcome you to the ARSET webinar on Introduction to Water Quality Monitoring from Remote Sensing Measurements. This is the second week, and as you may know, we have several sessions, so that's why the time says 8 to 9 a.m., but it is 1 to 2 p.m. Eastern US time. So this is the outline of the entire course. In the first week, we went over introduction to remote sensing, features that we need to know or attributes that we need to know about remote sensing, and background in water quality parameters. This week now, the focus is going to be on NASA water quality data available from various satellites and sensors and how to access these data. So there are web-based tools that help access these data. So we will go over this information today. Just to go over the usual information, I am Amita Mehta, and I've been doing ARSET webinars for a couple of years now in water resources management. Ana Prados and Africa Flores, they are doing Spanish webinar about water quality monitoring, and we have a guest speaker next week from EPA, Dr. Blake Schaefer. Our presentation URL is ARSET GSFC NASA Gov, and webinars or water webinars will get you to the webinar information page. Marina Martins is our helper. If you have any question about any material or any training information, please contact her or send her an email. And we want to acknowledge help from Brock Levins. He has helped us in various ways. In communicating with all of you who have registered for the course, and also in putting the course material together, as well as he is going to be presenting a case study next week. David Barbato is our Spanish translator, and Kristen Lee from Applied Science, NASA Applied Sciences, she has encouraged us to work with water quality webinar. So this is our website, ARSET GSFC NASA Gov, and on the left-hand side, the webinars link is there, and as shown here, this is the water quality monitoring webinar. Last week's presentations and recordings are already posted here, and today's presentations and recordings will also be posted soon. So please visit this site to get access to these presentations and recordings. So here they are, and this is our listserv. Please join it. It keeps up to date about ARSET webinars and training, upcoming trainings. So this brings us to week 2 outline. As we mentioned earlier, this is going to be an overview of data, access, and tools. So we'll start with overview of satellites and sensors that NASA has for remote sensing monitoring. We had an overview of that. We introduced these last week. We're going to go much deeper today, talking about attributes of satellites and sensors. Then we will go to water quality data and tools, and the tools are, several tools are mentioned here. These are web-based tools that enables one to access these data. We'll briefly mention which future satellite missions are planned. And then there's also a ocean biogeochemical model that NASA has that provides some of the water quality parameters. We will introduce that. So now this webinar being an overview webinar, there's a lot of information in today's session. We're quickly going to go through a number of satellites and sensors, and then the tools, how to access data. The objective here is to provide information about these and provide as reference information so that anyone who wants to refer to this, they can find what satellites, what sensors, what parameters, where to find them, and where to access them, where the websites are. So information is is a lot, and please bear with us as we work through it. And if you have any questions, we'll talk to you at the end. So this is what we saw last week. Water quality parameters marked in red, they can be obtained from NASA Earth observing satellites. These missions they span multi-year and they have near global coverage. We also saw last week how they complement in situ measurements because in situ measurements are quite infrequent and incomplete in space. So these data are quite useful that way. And all physical, chemical, biological properties, some of these data can be obtained from satellite remote sensing observations. So this is what we will be talking about today. Last week we saw what attributes need to know to work with remote sensing data. And so that starts with missions and sensors and satellite orbit configuration, because that decides temporal resolution, spatial coverage. So type of orbits we discussed last time, geostationary and polar orbits. We talked about sensor characteristics. So type of sensors, active or passive, spatial resolution, the number of sensors with different resolutions are available. And we talked about spectral bands of measurements. As shown here, this is the electromagnetic spectrum, and in which wavelength and how many bands are there. That also provides information about water quality parameters. And this shows just a figure of orbits from Aqua satellite. So we talked about these features last week, and these are the satellites and sensors we talked about, which are very useful for observing water quality parameters. So we talked about Terra and Aqua satellites. Both of these have sensor, it's MODIS, and parameters available from MODIS are listed here. It's chlorophyll concentration, temperature, CDOM, turbidity, and euphotic depth. We talked about these parameters last time. Landsat is another mission with sensors, thematic mapper and enhanced thematic mapper, and operational land imaging, as acronyms are given here. The parameter available here is spectral reflectance in different spectral bands, so images are also available. Terra also has a sensor ASTER that provides spectral reflectance and temperature. NPP, National Polar Partnership Satellites, has an instrument VIIRS that provides spectral reflectance, and recently they have put out chlorophyll product out as well. VIIRS is similar to MODIS. So what we're going to do is go through each satellite, talk about orbits, talk about each sensor, which spectral bands they have, what kind of resolution they have, and where to get this data, where to get more information about these data. We'll start with that. Then we will go forward to, there are two research missions currently in orbit, EO1, or Earth Observing Satellite 1, and that has Hyperion sensor. And right now, spectral reflectances are available from these instruments. HICO is flying on International Space Stations. These are research missions, so we will talk about them a little bit. And we will briefly mention past data, which is recent past, that stopped in 2010 and 12 respectively, these two. So these data are readily available, some of these parameters, so they can be used to look at trends or long-term variability compared to past and from past missions and also from current missions. So we'll go over that. So there are 2 points to notice here. Satellites such as Landsat has TM, ETM, OLI, as we will talk. Terra is ASTER, EO, and Hyperion. They all measure spectral reflectances in different bands. So these imageries, as we saw last week, can be interpreted in terms of changing water quality, but this is a qualitative information. Just by looking at images, one can sense how water quality is changing. However, to get further information, quantitative information about particular water quality parameters, there is more processing needed. Algorithms have to be developed so that, and in situ measurements are also used in there to derive relationship between satellite measurements and in situ parameters. And these relationships are then used in algorithms to convert all other satellite data into parameters. So more processing is needed. So MODIS is one instrument flying on Terra and Aqua. NASA has already processed some of the water quality parameters, and these data are readily available from web tools. So for this session, we will describe all the satellites and sensors and websites where these data can be obtained, but we will focus more on water quality parameters available from MODIS. Because they are online, they are multi-year and very easy to obtain and analyze. So we will focus on that in the end. Okay. So to start with, we talked about how changing images can provide information about water quality parameter. And here is an example shown. So these are blue, green, red, and near infrared bands, and how they relate to chlorophyll concentration. This is in milligrams per cubic meter. So less than 2 milligrams to up to about 2 milligrams. Blue and green chlorophyll change. These two bands provide information. Reflectance in these two bands provide information about chlorophyll concentration. This is open ocean and this is coastal ocean. So open ocean signal is very clear. There is no contamination of nearby land. So this is very clear in blue. In coastal seawater, this is more in green. And if we go further, when chlorophyll concentration increases, then this is the signal in red and near infrared. So reflectance is by observing reflectances from satellites in different bands, one can come up with qualitative information about where the chlorophyll concentration may be in particular water body. And this red spectral reflectance, it shows presence of algae in water actually. So there's a clear signal in red and near infrared when it is more algal bloom. So this is one parameter that is seen from spectral reflectances. Similarly, Secchi depth, height that can be measured similarly from reflectances. Turbidity or suspended material can also be similarly observed from different, just looking at different spectral reflectances. One example of using Landsat thematic mapper to convert to a trophic measurement that is a measure of nutrients and also chlorophyll. So this is Landsat thematic mapper data in spectral radiance, and in here it is observed in situ measurements, and this is state of Minnesota where about 10,000 lakes are there, and this article here describes how satellite data, in this case Landsat, and in situ measurements in a few lakes are used to derive relationship between water quality parameters and spectral radiances, and then these relationships are applied to different lakes and water clarity is monitored by using these parameters. So in similar fashion, Landsat and MODIS, both of these are they're widely used to monitor different water quality parameters as listed here. So to continue with this study can be found on this site. This is University of Minnesota, and they have a water resources center where information is given how satellite radiances or spectral reflectances are used in combination with in situ data to get water quality parameters. This example here is Ontario lake water quality. So this is a good resource to study. There is a lot of information about how to use remote sensing data, and there are practical applications applied on lakes in state of Minnesota. Okay, so with that background, we want to look at now all the satellites and sensors that are useful for water quality remote sensing. So we'll start with Landsat. Landsat is a continuous mission with multiple satellites. It started in 1972, as shown here. And so Landsat 1 all the way to Landsat 8, which was launched in 2013 February. So these are the missions that span more than 40 years now. And the sensors flying on these satellites also are listed here, such as the current mission that started in 1999, that is Landsat 7, and then Landsat continuing mission Landsat 8 that was launched in 2013. So current decade is observed by these two Landsat satellites, and these two satellites have ETM plus and OLE. So we will look at those sensors. But this is one of the longest flying missions, and it's been used quite a lot for water, land, and atmospheric applications. So this plot shows orbit of Landsat satellite. It's a polar orbiting satellite, and it has 10 a.m. equator crossing time, which means that at local 10 a.m. time it crosses equator. Similarly, at local 10 a.m. and 10 p.m. time, it observes location on Earth. So observations depending on either it is polar or this where you are located, there could be one, there are several, two observations per day, but same place is not covered before 16 days. So revisit time, so that means same piece of Earth observed by Landsat, that time is about 16 days. There is global coverage otherwise from pole to pole. And here the bands are shown where these are the visible all the way to, these are the bands that are used by TM, ETM, and OLE. Okay. So looking at sensors now, as we see each satellite we will look at will have several sensors. We are going to focus on the ones that are currently flying as well as which are useful for water quality parameters. So ETM Plus has 8 spectral bands, major in blue, green, red. So these are all useful for water monitoring as shown here. Reflectance signature in different Landsat bands are from soil and from land, and here is the part where it is sensitive to water quality. So this is what these are the spectral bands used for monitoring water quality. So ETM Plus has band dependent resolution, varies from 15 meters to 60 meters, and swath width. So that is the area covered in east-west. That is the swath width. So that is about 185 kilometers. ETM Plus is flying on Landsat 7, which was launched in 1999. So right now the data are available from ETM Plus from Landsat 7 and also operational land imager from Landsat 8. So this is called continuity mission, Landsat data continuity mission, or LDCM. And this has 9 bands, one more than ETM Plus. It has a panchromatic band, and resolution is 15 to 30 meters depending on bands, and same swath and same equator crossing time. And temporal coverage starts in February 2013. The bands are shown here. How they are. In OLE, there is one more blue band that helps in better contrasting in coastal ocean regions. Okay, so this is just an example that Landsat 8's new band, that's blue band included, has better clarity about, you can clearly see how changes, color changes, and that gives indication of water quality. So in this one band, so this is just one example. Now, from Landsat, only spectral reflectances and imagery are available online. Derived water quality parameters are not routinely available. They are available from research papers, but not in operational fashion online. So these are some of the parameters obtained from Landsat reflectances, and a number of research papers have been published focusing on regional water bodies, but online data are available in forms of imagery or spectral reflectances that we will see shortly. So from Landsat, now we move to these two satellites, Terra and Aqua. These are NASA's Earth observing satellites launched in 1999 and Aqua in 2002 respectively. These two are polar orbiting satellites. Terra has equator crossing time of 10:30 a.m. and Aqua as 1:30. So observations are here in Terra are in local time at any location 10:30 a.m. and p.m. and this is 1:30 a.m. and p.m. Both these satellites carry a number of sensors, but both have MODIS on it, and that provides multiple observations throughout the day. 10 a.m., 10 p.m. as well as 1:30 a.m. p.m. can be obtained from these two satellites. They both have global coverage, and as we said, it is a polar orbiting satellite. Okay. So MODIS, or Moderate Resolution Imaging Spectroradiometer, that we have talked about since last week, flying on Terra and Aqua, is a very versatile sensor, has been used for land, atmosphere, ocean, cryosphere, that is ice observations. So MODIS spectral bands, there are 36 of them, and they are used for different applications. The one in red, in blue and blue-green and near IR, they are used mostly for water quality sensing. The bands in green, they show where MODIS spectra. So this is the region where water quality parameter is sensed. Temporal coverage is from 2000 to present, nominally 2 times per day or 4 times per day if you look at two satellites. But resolution again varies depending on band. The highest resolution is 250 meters all the way to 1 kilometer. So the band used in this are about 500 meters. So this is the resolution used for water quality parameters. So this is an example again. So MODIS spectral reflectance is, just as in case of Landsat, are used for getting chlorophyll concentration, sediments, temperature, CDOM, turbidity, and one example shown here is in Green Bay, Wisconsin. Case studies, that these are all true color images. These dates are shown here from July to September. So it shows sort of a seasonal cycle during July to September. And so from these true color images, then Secchi disk transparency is measured in meters, and clearly variation in this transparency can be seen as season progresses. More information can be found about this study from this website, and a lot of information about MODIS instruments and spectral bands and other information can be found from LPDAC USGS site. Okay. Moving on to ASTER, which is also flying on Terra, has 14 spectral bands and has a near infrared band, so that is useful for monitoring surface temperature in water. The bands are shown here, and special coverage again is global. The swath width is a little smaller. It is about 60 kilometer. If we see compared to for MODIS, it is about almost 30 kilometers. ASTER is 60 kilometers and has resolution varying with bands again, 15 to 90 meters. And it also is available from 2000 to present. The next satellite is National Polar Orbiting Partnership, or NPP satellite. And this satellite it's the most recent satellite launched in 2011, and is a polar orbiting satellite with 1 or 2 observations per day. Several sensors. The one that is used for water quality monitoring is VIIRS, and this has equator crossing time of 1:30 a.m. p.m. similar to closer to Aqua satellite. So recently there is online availability of chlorophyll concentration derived from VIIRS, and we will review that too. Okay. So VIIRS, which is flying on NPP. So red bands shown here are from VIIRS and green from MODIS. So there are less bands, like 15 bands, but all major bands such as blue and blue-green and middle and near IR are covered in VIIRS. This instrument is similar to MODIS, and it is designed to continue parameters obtained from MODIS. Similar parameters can be obtained from VIIRS. So VIIRS is sort of designed to continue MODIS in time forward from 2011 onwards. The swath size is a bit larger, about 33,000 kilometers or so. And special resolutions, again, depending on band, it is 375 meters to 750 meters, a little lower than MODIS. And it's available since 2011. So now we're moving to 2 of the research missions that we talked about. So EO1, or Earth Observing Mission, that was launched in 2000 and has equator crossing time of 10 a.m., similar to Landsat. So it's a polar orbiting satellite, and it was launched in formation with Landsat 7. So both these satellites are used for validation of each other's observations. This mission was an experimental mission for 1 year, but now has been extended because of its usefulness. And this has data acquisition within minutes from Landsat 7, so it is providing a lot of information that way. Has sensors, and Hyperion is the one that has many spectral bands and can be used for water quality monitoring. So this is a new experimental mission. So Hyperion, as shown here, a lot of information again can be obtained from this site, and just a swath is shown here. This has about 220 spectral bands, starts in visible and then goes to infrared. There are about 28 bands between 480 to 750 nanometer, which are very useful for water quality monitoring. And these images are used for many applications because there are so many narrow spectra. Now there is one limitation. There is good resolution, just like Landsat is 30 meters. It has good coverage since 2000. However, these data are available through only data acquisition request. They are not operationally available as in case of Landsat or MODIS. So the dots shown here, these are archives of data from Hyperion. If earlier requests, when they're done, these data are then archived and they are available, but they have to be requested to get the data. So it is a bit involved process. And these shows example of like hyperspectral coverage versus multispectral coverage from Landsat shown here. So these are representations discrete representations, whereas here there are many more bands, so there is more information that can be retrieved. Okay. Another experimental mission is or sensor is Hyperspectral imager for the coastal ocean, and HICO. HICO also is not available operationally, it has to be requested. So more information can be found from this website here, and data request website is given here. There are 87 spectral bands from visible to near infrared wavelengths, so useful for monitoring water quality. Example shown here is the mouth of Columbia River, as one can see, and clearly where it goes into this ocean, that also can be seen from the satellite HICO image. So there is special resolution is 90 meter. That does depend on how altitude and angle at which piece of Earth is looked at from space station. There is, if the request is such that only one image per orbit can be requested, and any scene is usually 42 kilometers by 192 kilometers. So there is high special resolution, reasonably good resolution, and scenes can be requested, but this is also a research mission. It's flying since 2009 September, and the revisit time is about 3 days. So Hyperion and HICO, there is information given here, but these are research missions, and operationally data are still not available. Only radiance spectral reflectances are available. Okay. Now we've talked about current missions, Landsat, Aqua, Terra, and we talked about 2 experimental EO1 and HICO. These 2 we talked about. Now, just to mention past ocean color missions, one is SeaStar OrbView satellite, which has CWIF sensor. This covers 1997 to 2010, and this is also polar orbiting satellite with 12 p.m. equatorial crossing time, almost global coverage. NVSat, which is European Space Agency's satellite, also VIIRS, flying with other sensors used for water quality monitoring, especially ocean color. That was launched in 2002 and stopped working in 2012. So it has 10 a.m. equatorial crossing. So these 2, CWIFs and VIIRS, as bands are shown here, this is VIIRS, this is CWIFs, and MODIS is shown in comparison. So these bands in visible and near infrared are pretty much similar, and these missions, especially CWIFs and VIIRS, were designed so to clarify the magnitude and variability of chlorophyll and primary production, and by primary production by phytoplanktons in oceans, open oceans to start with, and then coastal oceans, and to see timing of algal bloom based on that. So 8 spectral bands in CWIFs, both, and VIIRS has 15 spectral bands. Both have about 1.5 to 1.1, 1500 to 1100 kilometer swath. Here is 4.5 kilometer. Here resolution is 260 meter to 300 meter for coastal oceans. Over open oceans is almost like a kilometer to 1.2 kilometer. So different sensors, all of them are in polar orbiting satellites. They all have different resolutions, pixel scale resolutions, and they have different spectral bands, slightly different characteristics. So these are the past missions, and we mentioned here because these data are available online to look at past to present variability, and it provides also data are useful if there are in situ measurements in the past. These data can be used to develop algorithms, and then that can be applied in current and can be tested in current situation as well. So that's why these satellites and sensors are mentioned here. So as we talked about, different sensors have different special resolutions and different temporal and spatial coverage. So any remote sensing product, before using it, is being processed. So there are usually different data levels available for remote sensing products. And here is a summary of how data levels are defined and what they provide. So for any remote sensing sensor or any instrument, level 0 data means raw instrument data. It is in terms of digital counts, perhaps, and then or radiance, and then it is converted to or reflectance, and then it is converted to level 1 data, which is calibrated and geolocated reflectances or radiances. So they are assigned let alone for each pixel. Level 2 is further processing, and here is where algorithms come into play, that from calibrated geolocated data, now geophysical or biogeochemical physical data for water quality parameters are derived. Based from this, now these are converted to actual physical parameters such as chlorophyll or serum or turbidity can be obtained from level 2. Still, all these data, they are orbital data. So each pixel is resolved and it is along the orbit. So we saw that there are orbital gaps. So that is also there in this data. However, there is more user control for taking this data and then analyzing to meet your own needs. So there is more control that can be done. This is the highest spatial temporal resolution available. And they're somewhat harder to use because they are non-uniform in space and time. And it's a lot of data sometimes to look at, very high resolution pixels to look at. So there are processed products available. These are level 3 data. And level 3 data are composites of level 2 data. So they are geophysical parameters, but they are now gridded. And they're gridded so that they are on a uniform spatial resolution grids. They can be available on multiple spatial and temporal resolutions. So say from twice a day orbits, these data are composited so that there can be daily data. So instead of pixel resolution of 250 meters, it can be put on several kilometer square grid, as we will see in case of MODIS. So that is level 3 data. And they are easier to use because there are quite a few, there are web tools developed. They're easy to access as they are uniformly gridded. And there are analysis and visualization tools also available for level 3, several level 3 products. Level 4 data can be model derived data in which satellite data may have been used. So these are the data products levels. And what we're going to talk about is level 3 data. Although we will see some level 1 and 2 how to access those, mostly we are going to focus more on level 3 data as there are web tools available to access these data. Okay, so any remote sensing data, there are several formats, different sensors and different missions, they provide data in different formats. Some can be available as text or ASCII data, which are just human readable on computers. They're easy to read and examine, but they can be very large for large regions. Looking at numbers may not be easy to analyze. They can be manipulated with Excel and GIS software, however. So the more common data used for, especially for global satellite data, is binary file format. It's either HTF or NetCDF. These are the formats. They take less space and information about metadata. So attributes to all these data, how they're processed, what kind of resolution, they can be included in the file, embedded in the file. And they can be read on any machines. So these are some of the pros. Cons are that they need tools to read, so need code to read these files. They're not readable like ASCII files. There are KML or KMZ files available. These are mostly for visualizing data. and they can be used with Google Earth. So they are easy to quick look at any data. So this is also, there's a low data volume. So these are good to quickly monitor, quickly look at any images. Occasionally, some data are available as shape files or GeoTIFF images, so there can be direct application in GIS. Not all data are available in this format though. So these are all formats, so any can be used. So we looked at satellites and sensors, we looked at data levels, and now we want to talk about data access tools. So there are two points to note here. One is that initially we will look at the data that are level 1 or level 2 or imagery, and so especially Landsat and EO data, which are not available operationally in terms of water quality parameters, how to or where to get those. And then we are going to go to NASA data, especially MODIS data available through several tools. We want to point out this webinar that was conducted earlier, a couple of months ago by ARSET. It provides information about a number of tools to access NASA satellite data products, especially Earth Observing System Data and Information System. They have about 12 data centers and number of tools. Sometimes software is also available to access data. So this is one useful resource. Okay, so what we're going to do is we are going to look at a few tools listed here. So for Terra and Aqua MODIS, we're going to look at a tool called Giovanni. This is and CDAS or Ocean Color Web. These are both available from NASA Goddard Earth Science Data Information Services. The water quality parameters are available here, and they are gridded data. They are level 3 data at 9 kilometer and 4 kilometer at 8-day and monthly composites, and multi-year coverage is available. So MODIS level 1 and 2 data and also level 3 data are available from Ocean Color Web from here as well. We will look at these two tools. There is daily 3 to 8 day monthly composites, and these are also gridded data. Level 1 and 2 are the pixel level data. Now Landsat, so TM, ETM, and EO1 Hyperion, Terra, ASTER, only spectral reflectances are available online operationally. These can be found by using these tools. LandsatLook Viewer, GLOVIS, and Earth Explorer, these are USGS tools. And there is coverage, so images are available in highest resolution. NPP VIIRS is available from a STAR tool that is from NOAA. And this is a recent addition to our toolbox, and we're still working on it. The Chlorophyll is available from this, and so are spectral reflectances. The resolution is also the highest, 375 meter. So level 3 data are gridded. Everything else is really the pixel resolution is available. But then level 3, there are derived parameters that we will see. Level 1 and 2, and here these data are just spectral reflectances. They have to be further used in algorithms to get quantitative information about water quality parameters. So these three shown here are USGS tools, and they are useful for acquiring Landsat images. LandsatLook Viewer, specifically designed for Landsat data, it is useful for visualizing as well as accessing data. And as shown here, which satellite data that can be picked here. Time can be picked here, year and day. There is a number of, there are quick guide given here. There is special search here, and then image display or data access can be chosen, and then this data can be accessed. These are level 1 data products, and GeoTIFF image is available, so can be used with GIS as well. The second tool is GLOVIS. GLOVIS also has, it provides Landsat data tile by tile, and there is a row and lat long selection here. There is time selection here, and there is a quick and easy online search tool for satellite data. It can have map layers. There are a number of tools available. So this is something to explore. For the time limitations, we are not going into detail, but this is a, ARSET has a land management webinar going on, and online presentations talk about these tools, because Landsat data and these tools are useful for land management as well. So we refer to that, and we will post the link for that webinar, land webinar as well, to to learn more about these tools. The last tool that provides not just Landsat but ASTER and EO1 Hyperion data is Earth Explorer. This also is based on this is one way to get multiple satellite data, and one can choose from which data sets to use. So there is search criteria given here, and there are path, rows, or lat-long can be chosen, and their data range can be specified. So number of images available in that range are then given through Earth Explorer. Now this tool, Proc Blevins will be demonstrating next week, because this is useful for all Landsat EO1 and ASTER data. They all can be obtained by using this. So we will have a demo of this tool next week. This is a NOAA tool. This is for acquiring VIIRS data, and there are color composite, ocean color composite images given here. So Chlorophyll A is there. There are several experimental products. Also, there is MODIS Chlorophyll A. So for comparison, these two are available. It could be global or regional. There is a selection for region, and there is temporal selection here given as well. So this is a new site that we are also just exploring, but here's the web address, and one product that is available is this, and there are other several experimental products as well as spectral reflectances are available from VIIRS. So this brings us to our MODIS water quality parameter data using a number of tools that NASA has. So this is without really getting any spectral reflectances or using algorithms. In first approximation, these data can be used for looking at several water quality parameters. And so we're going to start with a tool or a website, which is CDAS. And this site has been around for a while, and several versions are there. This is CDAS 7.1, and a lot of information about missions are given. Data of different levels are available. There is data access for all these. So MODIS, there are past data available as well, CWIPS and MERIS, and these are also historical missions that we did not have time to talk about, but they are past missions as well. But these are the data, these are current data available from this. Analysis and other links are also provided here. So this is Ocean Color Web. This is the website, and this provides information about level 1 and 2, level 3 data for a number of sensors. We will see this soon. If you just bear with me, I would like to share my screen, show you this site. So this is the Ocean Color Web CDAS site. And all the mission information is given here. There is user support area. And here is all the information, the documentation about data products. There are publications, there are software and tools available for different applications are here. For analysis based on level 3 data, so trends of ocean color that is available, calibration, validation information is available here. And so just to show an example, this is the ocean color web that provides, again, data in level 1 and 2 as well as level 3. And just to see level 1 data, number of sensors are available, CWIFs and MARIS from past, Aqua MODIS and Terra MODIS are available, and VIIRS is available. These are available, so our HICO, whatever is available, some images are there. And there are some past missions here. There is a way to pick region or coordinates. There is a calendar. Aqua was launched in 2002, so all the way from there to now, daily data are available, and parameters like this particular is chlorophyll concentration shown here. So clicking on any day, this is the level 1 data now for Aqua MODIS, and this is pick any point, September, this is September 2004, 11 September, and clicking on any region. So this is the region we are currently looking at, and this shows chlorophyll concentration in sea surface temperature. This is the true quasi-true color image, and then there are ways to look at the data themselves, or either in compressed files are provided here for regional data, so they can be downloaded and studied further. But visualization can be done regionally and for days from 2002 to, so this is all high resolution data for level 1 data. Similarly, level 3 data are also available, and this is again chlorophyll A concentration. In the scale is given here, and so this is November 1, 2014. So these are again so there is daily data, there is 8-day composite or monthly data available, and these are the monthly data. So October to this latest month available here, so they are quite current, and bear with us while it's getting to the image. But then this is monthly October 2014 chlorophyll concentration can be seen over global oceans, as well as large lakes can also be seen in here. Here is the Great Lakes, here is Lake Victoria seen here. So Mediterranean Sea. So larger water bodies are all, inland water bodies are also visible, and open ocean, of course, and coastal oceans are sensed very well here. So this is an example of how data can be obtained or visualized. There are archives of data. There are past data, similarly can be obtained. And there is, this information is provided. For limitations of time, we cannot go through each feature, but one can study if the data are needed or required for particular applications. And also, now going back to my presentation, Bear with me for a minute. Okay, so we saw a quick demo of how to go through Ocean Color Web and look at different sensors and different levels of data. Another tool, this is a Giovanni or tool that is from Goddard DAC or data center. It has a number of portals from hydrology to meteorology, but there is also ocean portal that we want to look at. And by selecting that ocean portal, Giovanni Ocean Portal takes you to level 3 data from MODIS. So water quality monthly data and 8-day data are available. And number of data parameters can be selected as shown here. So there is special selection through map or through coordinates. And there is temporal selection from here. A number of analysis options are available. And so it can be mapped, any region can be mapped, or time evolution can be seen depending on how many months one specifies here can look at time evolution. And we will see an example soon. Images can be animated to see how water quality is changing. So all these app options are available. Giovanni also allows downloading of data. So again, I would like to share my screen with you and show Giovanni. So this is the Giovanni site, and here's the ocean portal. So these, let's look at water quality monthly data. And one can see that data are available from past CWIFs. They're available for MODIS, Aqua MODIS at 9-kilometer resolution and at 4-kilometer resolution as well. The parameters available are listed here, can be chosen by clicking here. And sticking to chlorophyll concentration again, here any region can be picked by drawing and any time can be picked here. So generating visualization here can give us chlorophyll concentration over selected region for selected month from Aqua MODIS. This particular plot will be at 9-kilometer resolution, and it shows a change in chlorophyll concentration over this region. Once this is created, there is a way to download data. So visualization and analysis can be done, and then data can be downloaded. So the same data that was used in making this image that we just saw, that image is available, as well as that monthly data from MODIS Aqua chlorophyll concentration at 9-kilometer is available in HTF and NetCDF format, and that can be clicked and downloaded. Also, available are KMZ files. So these are the files went into creating that plot. And here is the KMZ file that is downloaded, that can be downloaded and viewed in Google Earth. So through Giovanni, it's a popular tool for a number of portals, but Ocean Portal, of course, helps look at one more example can be, suppose a small region can be chosen over ocean, and how chlorophyll concentration varied over last year, that can be checked by looking at time series. And these data again can be, these time series data will also be available through download data section that we just saw. So this shows how over this given water region, how chlorophyll concentration varied from January to December in this 2010, but a long time series can be viewed to see variability and change over any region. And we will demonstrate that next week when we look at some regions where we will look at time evolution of different parameters. So going back to the presentation, so all the data that we saw, MODIS level 3 data and level 1 and 2 data are available through these tools, Ocean Color Web and Giovanni, and they can be visualized and can be downloaded for any region. So that brings us to our future missions. These two missions are planned, especially for continuing ocean color measurements. And GeoCape is special because it is one that will be in geostationary orbit that will focus on 95 to 100 west, so it focuses over the North American region, and proposed resolutions of ocean sensor will be about 250 to 1 meter to 1 kilometer, similar to MODIS, but now this is a geostationary orbit, so it stays focused on this region all the time, so can have multiple observations throughout the day. So this will have a very good temporal resolution, better than any current sensors. And this will be used for measuring phytoplankton in coastal oceans and other processes in oceans. So this is under planning, and PACE is going to be a polar orbiting satellite. This is also planned for 2019, and we'll have ocean ecosystems focus on that. And we'll also have visible and IRS spectra. This is all under development, but this will continue what MODIS and VIIRS are currently measuring. This will continue in the future through these missions and even will be improved. So finally, we want to talk about a modeling effort that NASA has for ocean biogeochemical modeling. There is a model developed, and this has multiple components. It has biogeochemical processes and circulation within ocean. So it's a ocean circulation model where processes are modeled, and it has atmospheric forcing given also from a model plus satellite observations. So winds, SSTs, dust, sea ice, CO2, all these are prescribed in the atmosphere. And then in the ocean, there are multiple levels and circulation, and these processes are modeled. And in these are the parameters available in output. These are all, again, model data. Some of the processes included here is how nutrients and planktons interactions occur. So this is a complex model, and again, it is just using these processes within ocean circulation model. Has an explicit carbon component as well. The resolution of this model is 1.25 degree longitude to about 2/3 degree latitude, and there are multiple levels, but for water quality, it's the top surface that is more important. The atmospheric forcing uses a number of satellite and remote sensing data. There is a version of this model in which CWIF's data are assimilated. So this model provides a number of parameters, and it is available in Giovanni as well, as we will see in a minute. But this is more to understand processes that occur, and then they determine water quality of ocean surface water. So this is a comparison shown here of the modeling chlorophyll concentration in milligram per cubic meter. This is from CWIFS, this is from Aqua MODIS, and this is from NOAA in situ measurements. So there are differences among different sensors, but still they compare pretty well with fairly good correlation here with CVIFs. And so this is a comparison shown here. And this model data, some of the parameters are water quality parameters can be looked at from these biogeochemical model. It's again available from Giovanni. And so this is one model that is global model and provides insight into processes that go on that decide water quality. So that brings us to our conclusion of this webinar. And this is the next week's agenda. We will have an invited talk by Dr. Blake Schaefer from EPA. He will review the field of water quality monitoring from remote sensing, where it is and where it's progressing, etc. We will have two case studies. Dr. Africa Flores from NASA Surveyor will show how to monitor water quality in a lake in Guatemala, Lake Atitlan. And then Brock Blevins and I will look at Giovanni and Earth Explorer to look at MODIS data as well as to get Landsat data for Lake Victoria region in Africa and to look at some water quality parameters there. And so this will conclude our course next week. So now I want to thank you all for attending this presentation. There is an appendix given here where information about water quality models in the US, and these are USGS, EPA, and USDA models. So information can be found here. And there are also details about spectral bands and satellite sensors are given in this appendix. This webinar was again aimed at providing overview and a lot of information about like which sensors, what characteristics, where to get, what data levels, what parameters, etc. Each tool or each data set or each case studies can be looked at in more depth, and that is why ARSET also conducts advanced webinars and hands-on trainings. So those are regionally focused as well as focused on particular data or particular tool. So please keep that in mind. There is a way to apply for advanced training or hands-on training on any of this topic. So thank you again for attending this session, and if there are